Yeah, so I'm Micah Carroll. I'm a PhD student at UC Berkeley, and today I'll be talking about UniMask, Unified Inference and Sequential Decision Problems. That is a project that I worked on during an internship at Microsoft, but then like kind of spun out into its own whole thing. Yeah. So okay, so basically, we've all seen how like treating language as a sequence modeling problem has been very successful in NLP. What does that mean? Well, basically treating individual, like, or splitting language into, or treating it as different tokens that then we just pass in large language models. And then we have these language models try to predict, I guess, potentially missing inputs as in BERT. So this is kind of like the close task in BERT that is one of the most commonly, well, I guess like one of one of the important language models, I guess, of the recent years. And so what BERT does is that it tries to reconstruct or fill in the blanks essentially for inputs that were masked out at inference time. And this is what it's trained to do. And it basically generates very good embeddings for downstream tasks. And so I guess like there's been some previous work, actually also from Berkeley, that's been basically focused on thinking about whether this type of paradigm of considering languages as a sequence problem can also be applied to sequential decision problems. So basically considering sequences of state actions and rewards also as tokens or as sequences from which we can mask out certain certain components. So okay, so they didn't actually consider this idea of masking out portions of the inputs, but they thought about, okay, can we use this or can we consider state actions and rewards as sequences for generating high reward sequences. So I guess yeah, what we try to consider is can even this principle of masking be applied in this kind of context? And why would we want to do this? Well, you can also, again, kind of feed in these types of sequences to these transformer models that are used in language, and then try to predict missing components of the input sequences. And this actually enables you to do, or it's much more general in some sense than what these previous works were trying to do. So let's try to break that down. So in particular, let's consider this specific task of predicting action one given the initial state and the initial two states and the initial action. So this task is basically going to be equivalent to trying to train your model to make this kind of inference of what the first action is given this history or this past context. And this is equivalent to basically performing behavior cloning. So yeah, one could say, okay, well, behavior cloning actually there's multiple maskings, I guess, that correspond to behavior cloning in this type of setting, because you have to consider both when you have your initial state, what's your initial action, and then you can kind of autoregressively reuse your model with different types of maskings in order to get this later actions and basically sample your trajectory. But yeah, so essentially, I guess the main thing that I'm trying to get across here is that for every masking that you can apply to your input sequence, there will correspond an inference task that you're trying to train your model to perform. Okay, so I guess I'll just switch to this kind of other more compact representation, just because it will come in handy. But yeah, so one thing to note is that this type of masking paradigm is very general in the sense that many common tasks that one cares about can be represented as specific maskings. So not just behavior cloning, so kind of imitating an expert can be represented just as a masking, but also things like reward conditioning or offline RL. So this is what the prior work had focused on specifically, but also things like goal conditioning. So you also mask everything in the future except for the final state. And what you're basically training your model to do is to predict actions that are going to lead to that final state, essentially. And this can also be applied for waypoint conditioning, past inference, future inference, You can also express forward dynamics or inverse dynamics as maskings. And so there's a lot of like many tasks that one, or any inference task one can think about, essentially can be expressed as a masking in a very flexible way in this type of paradigm. Okay, so I guess like in terms of usages, well, behavior cloning can be used for doing like for creating better human models. Reward conditioning or like offline RL supposedly is should be helpful for kind of doing some kind of approximate policy improvement. Waypoint conditioning could be used for doing behavior offerings, so kind of like creating human-like waypoint condition trajectories. Potentially past inference could be used to estimate likely causes of failure if you condition on failures at the last time step and you try to infer what likely causes of those failures were, essentially. But many more tasks can basically, or many more inferences can be represented, and they might be useful in the specific application that one is working on. So, okay, so one question that naturally emerges when one considers this type of paradigm is, okay, how should I be performing training? So the most obvious thing is, if I'm just interested in a single task, say behavior cloning, there will be multiple maskings that correspond to that task. And I could train my model just on the maskings that correspond to that task. And yeah, I guess like another thing that like this type of way of thinking about inferences in sequential decision problems really lends itself to is training on multiple maskings at once. So one just kind of randomizes over the maskings for multiple tasks. And in this way, you can obtain a multitask model by basically training on multiple tasks at training time, but just randomizing which one. But an additional type of paradigm that we considered and is kind of like even more extreme than multitask is just randomly masking inputs at training time. So the remarkable thing here is that if one is training on randomly masked inputs, it's essentially equivalent to training a single model on all possible inferences in a sequential decision problem, because all these various specific tasks that can be represented as a masking will eventually come up at training time if you're randomly masking the inputs. So they have some probability of occurring. And so in a sense, you're training your model on these tasks and many others that are just very unlikely, I guess, they're all like almost equally unlikely to occur, essentially. And so, yeah, I guess like the promise here is kind of, yeah, like quite big in the sense that you can train a single model to perform any inference task in a sequential decision problem. Okay, and then I guess another thing is that once you have this kind of like random masking pre-training can be considered as like, yeah, I don't know, I guess it's amenable to the types of things that we do as pre-trained models. So we could decide to fine-tune this kind of random mask pre-trained model on individual tasks later on. So it's like continue training on specific tasks of interest. And this generally in NLP improves performance. And we thought that maybe it should do that here too. And I guess that's what we did find. Okay, so yeah, so I guess there's multiple ways in which one can train this type, or these types of models when you start thinking about multiple tasks as just maskings. And most of our work basically investigated the various pros and cons of the various training techniques, or I guess investigated the relative performances. Okay, so I guess like one of the first type of setup in which we test or we perform experiment is this kind of like simple mini grid environment where there's an agent and a key that are randomly initialized, and the agent has to go to a goal location, passing through a locked door which has to be unlocked with a key, and the agent has got some like chance of performing wrong actions and so on. And yeah, it's a pretty short horizon task. There's only 10 time steps of horizon. And then we try different data regimes. But for more details, I'll refer to the paper. Okay, and this is just a simple enough kind of like setting to experiment, but complex enough to have all the inference modalities that we care about have like some, like, or make sense, I guess. Okay, so what we find is that we can actually train a single model to perform all tasks, or any task, I guess, at once in a zero-shot fashion. So training with this kind of random masking, you can like query the model in various ways just by changing the masking appropriately. And you can get behavior cloning trajectories or goal condition trajectories or reward condition, waypoint condition, backwards inference, all with a single model that wasn't like, I guess, specifically trained to perform these tasks in any specific way. Like it was just trained to perform everything. And in fact, it can also perform tasks that we generally care about, I guess. And this was kind of surprising, even though, of course, this is a relatively simple setting. So maybe it's like less surprising in that sense. But one thing that we found is that also, so this is like a bit hard to read of a graph, but the main thing here is that each column has been normalized, and the value of 1 is the best performing model. And we see that when you train with random masking and then you do an additional round of or some additional fine tuning, you get best performance in basically all of the tasks. So essentially, you can do better than training. Like, so the elements on this diagonal are when you train on a specific task and you evaluate on a specific task, and you can do better than just training and evaluating on the same task by randomly masking as a pre-training and then doing a fine-tuning, additional fine-tuning later. And in fact, by looking at comparing some of these diagonal, okay, so I guess this is what I was saying. So like basically if you do random masking and then fine-tune, you can do better than the specialized models. And that is like may or may not be somewhat surprising, but I guess it's less surprising than the second result, that sometimes even if you just do random masking pre-training, so you're just training your model to do everything rather than specialize in any specific downstream application, then sometimes you get better performance than the specialized models. So this single model that is queried across all of these tasks sometimes does better than specialized models for some of the tasks. And we found that to be quite surprising. And yeah, so I guess like why would we expect like random masking and then potentially even additionally fine-tuning to do better than specialized models? Well, it's kind of like surprising maybe because you're using the same amount of data and in fact you're training your model on many more tasks. But we see that basically across most tasks, if you train with randomized masking, you get less overfitting during training, while training on a single task tends to overfit quicker. So basically, we think it's probably some kind of like auxiliary task data augmentation effect that enables the model to, I guess, learn more about the environment from the same amount of data and how the environment tends to work, and waste less of, or basically overfit less on the specific task of interest. Yeah, okay. We also have this other experimental setting where we test we test our method in a continuous control environment where we have non-Markovian dynamics. And yeah, basically it's a navigation task where like one of the dots has to move towards the other, but it's like a continuous control task. So like basically the action space is like continuous accelerations. The state is like the continuous location of the self and the goal. The reward is the distance covered. And also there's like random initialization of both the start and the goal state. And yeah, there's this non-Markovian policy. And we see kind of like similar results here, that even like training on multiple tasks and then fine-tuning can give better rewards than training on single tasks. And yeah, but one thing that we do see is that when you increase context lengths, the performance goes down a decent amount. And I guess like, yeah, the reasoning there is that essentially by just doing randomized masking, you're going to increase the amount of tasks that you're training your model to perform exponentially as the sequence length increases. And so that's like pretty challenging for models in especially in like more complex type of situations like this one. So that's like one thing that should be investigated by future work. Another thing we notice is that yeah, I guess like we baseline also against decision transformer, and we also I guess, made some modifications with like the insights that we had from our method to generate kind of like an improved decision transformer type of model. And we found that that can perform sometimes similarly to our method. So I guess like there's some idea here of, or we have some ideas here of how we could combine these, I don't know, like these insights from using a GPT or a decoder only model with our randomized masking to potentially get the best of both worlds. Okay, so I guess like in terms of limitations of our method, well, they're relatively simple tasks that we consider, and they have pretty short context lengths. And so that kind of informs our future work. So of course, yeah, we would want to scale up to more complex domains, use decoder only models that are much better at generation. And so we expect that that's why like our decision GPT model is like basically can perform sometimes like as well as our randomized masking model. And also, yeah, exploring alternate randomization schemes seems like a very a potentially very useful type of thing to do, just to be able to scale to larger context lengths too. And maybe explore multi-agent applications. Like it seems like there's many things here that can be done with like this kind of masking paradigm where you're trying to query how other agents will behave based on like specific behaviors of other agents essentially. And yeah, and it's very easy to test like various, like any hypothesis people might have out. We have our code that's like publicly available and pretty easy to play with. So we encourage anyone to do that. And yeah, so I guess like just summarizing, Unimask is a framework for flexibly defining and training models. And yeah, it enables to naturally represent any inference task and support multitask training. It allows single random mask pre-trained models to perform any task zero shot, or at least that's what our experiments suggest. And it can improve performance on individual tasks with multitask pre-training and additional fine-tuning. And yeah, so thank you all for listening, and thanks to all my wonderful collaborators.
Great, thank you. A quick question.
Yeah.
Is your method of training is used for generating like ChatGPT, which is like what's going on right now? So
yeah, I mean, I guess it's similar in the, or the model architecture is similar in the sense that instead of training on words, we're like, I mean, basically that it's the same model, but instead of using words, we're feeding in like states, actions, and rewards. So like kind of like environment signals, and trying to model how states, actions, and rewards tend to correlate with one another, in the same way that ChatGPT is trying to model how different words in a sentence correlate with one another, essentially. Yeah.
I guess ChatGPT has to train on a huge set of data that, with very large data sets. Does that affect the model at all, or it's just more crunching time?
Yeah, so I mean, yeah, so I think it's definitely true that like for NLP or like for natural language, like having very large data sets is very helpful, or like has basically enabled these models to become like much more capable. Yeah, I think like, I don't know, in this case we consider like relatively small data sets in these kinds of domains, but I think there have been like some attempts at trying to, like, I guess in sequential decision problems, what one could do is try to aggregate different data sets from different environments. So I don't know, maybe you have like some thousands of trajectories in this environment and some thousand in this other environment and some thousand in like some other game and so on. And you could train among all of them at once, to try to get a single kind of general representation of sequential decision tasks, in the same way that you can get a general representation of language in language models, even though you're training from like multiple types of, I don't know, like maybe you're training from Wikipedia, from books, and like from I don't know, different languages and so on, that all seem kind of like a little bit different modalities. I think it's harder in RL or in these kind of sequential decision problems, because like a lot of the sequential decision problems look very different. while, or like there's maybe less commonality like compared to language or different instantiations of language. But yeah, I mean, some people have already tried to do that kind of thing where you're like training multi-game decision transformers or Gato. Yeah, I think like it's still definitely lagging behind natural language. I think like natural language just lends itself to this type of thing more. But I think, yeah, I don't know, hard to know how well it will work within, or I mean, I'm sure there'll be improvements in the next couple of years, but hard to know how much. Yeah.
One thing that kind of course, people say it's magic is you ask ChatGPT a question and they will write an essay for you just from your question. Now, how does that relate to training? I mean, how does that happen, I guess?
Yeah, I mean, I guess like, so yeah, with ChatGPT, it's a little bit harder to know because there's two levels of training in ChatGPT, or potentially, I think I'm at least two, I guess. So the first objective is just to predict the next word. So it's like, okay, I've seen a bunch of sentences before, and like, how does the next word relate to the previous one, or like, how does the next paragraph relate to the previous one? So in a sense, it's like on the internet, if somebody asks, can you write me an essay about blah blah blah, maybe in the same website there will be somebody that wrote the whole essay, right? And so like in a sense, like it's learned how text follows, like or like certain text follows from other text, right? But I guess like, yeah, there's this additional layer of training that's being done to make it better at instruction following, and that's using kind of like reinforcement learning and like people giving feedback, explicit feedback of like, okay, the system gave an answer, or like basically generated the text, and then somebody said this is good text or this is not good text relative to the prompt. And so that kind of shapes the types of responses that the system tries to give towards, I guess, more likable responses. So in part, it will learn, okay, like this is like, I don't know, essays tend to be well received when they're written this way, or like when they're long enough or something. But in part, it will also learn to like try to trick the person to think that it's a good output, even though it might not be a good output. So maybe it's using more, I guess, more serious language, or more like authoritative sounding language, even though it's saying something completely wrong. But then that tends to make people click that it's a good output. Yeah.
So I understand better. There's a basic training that just be able to generate words that follow each other reasonably, and that's
Yeah.
so that level is a basic capability, and then you have a high level of a little bit more intelligence, seeing how other people answer your question, and then pull in input, and then from that construct an essay or whatever to respond. And maybe
Yeah, basically.
yeah.
Hey, Micah. So you touched a little bit on the natural language. So how much of the masking operation or transformer, how much of it is really language dependent? So how would it apply to language such as Chinese or whatever? So non-Romanized language.
Yeah, so I mean, I guess like, okay, so just to clarify one thing. So ChatGPT and like most of these chatbots that are, I guess, more well known today, like they're not actually based on masking. So that's more of a kind of like a slightly older paradigm that I think is maybe making a bit of a comeback. Like I think now people are thinking of using masking together with like, I don't know, GPT type architectures to improve performance further. But yeah, so I guess like I don't think GPT has to deal with any masking. The main thing is just tokenization. So that means is like, how do you cut up words into like specific components? And I'm not entirely sure how it works with like Chinese characters, for example, or like I guess I don't know, I guess like, yeah, I don't know how you call the like a Western alphabet or something. But yeah, I guess like, so for like English, like I think it's, yeah, I'm not entirely sure how tokenization is determined or like how to cut words. I think most words have their own token, and maybe even some like pairs of words have their own token if they're like sufficiently common. So yeah, I'm guessing you'd probably just, I don't know, I'm guessing you'd have like a token for each character, like each Chinese character probably. Yeah.
Combination of tokens, probably.
Mm-hmm.
I
Yeah,
mean,
maybe.
combination of words into one token.
Right. Yeah. Yep.
Yeah, I see English words and Chinese characters share similarity. If you know, each word will represent something, and sometimes two words will represent something, so it can be all tokenized in
Right.
the same methodology, I guess.
Mm-hmm.
We're
Yeah.
just learning.
Yes.
It's
So if GPT uses your masking, then it may improve on the operations then.
Yeah, potentially. Yeah, I think that, yeah, there's this paper that's called UL2 that's basically unifying learning like language paradigms, or something like that. I forget the exact name, but yeah, they showed how basically masking can be like, there's multiple types of maskings one can do even with GPT like models, and that can improve things, or that's my understanding of that paper. But I guess, like, I don't know, it seems like, yeah, masking might be having a comeback sometime soon, I guess. Yeah, even in language, where I guess it's mostly, I don't know, mostly for people like generating language, people have stopped using masking. Yeah.
This is kind of a broad question. You know, everybody's talking about AI safety and AI ethics.
Yeah.
With the approach, how do you see that potentially can happen, or it really cannot happen clearly?
I don't know. Like, I guess yeah, I think I don't know, I have mixed feelings about it, or I like mixed opinions about it. Like, I think, like, in some sense, yeah, I don't know. It seems very, or I mean, it depends exactly on what you mean by AI safety also. Like, I think, like, there's already, even with just current systems like Sydney or GPT-4, or, you know, like, I guess, like, even with the current paradigm of doing things, if things are just scaled up more, and, like, I don't know, basically all the investment that is currently in the field, like, having that play out in the next couple of years, even if there was no extra development, or, like, I guess, improvements in terms of like actual techniques, it seems like that, I don't know, that could already be very impactful, I guess, on society, in some sense of, like, I don't know, a lot of things seem relatively automatable by, like, translating the task into text and then having GPT-3 do some version of that, and then translating back to the task domain. So I don't know. I guess, like, in general, it seems like there's a lot of low-hanging fruit of things that could be, I guess, automated, or I guess, yeah, just yeah, by even the current systems. And, like, I think in the next couple of years we'll see a lot more of that. And that's, I don't know, I feel like that's, I guess, again, mixed feeling, like, in the sense, potentially, in some sense good, in some sense bad, and, like, I don't know, like, it's all very complicated or hard to really wrap one's head around, and really anticipate, but, like, both pros and cons, or I mean, I guess, whether the pros outweigh the cons, and or vice versa.
Yeah. My thinking is that, you know, you would detect certain words that are suspicious, and if GPT or the software has actually some appreciation of the context of what it's being said, that at some point the system could say that this is something that we need to be careful about. In fact, today, if you ask GPT some questions, ChatGPT, they would say, no, we cannot answer that, or this is not.
Right.
So
Yeah. Yeah, I guess, like, there's been a lot of, like, or I mean, it seems like most of these attempts, like, can be gotten around. Like, people have found prompt injection attacks where, like, I don't know, you're kind of convincing the model to still say all the bad things that, like, it's trying, like, they've tried to train it to not say. So I don't know, like, in general, it seems like, I don't know, if one wants to use these models for nefarious uses, it's probably relatively possible.
Mhm.
Like, and I don't know, and it's kind of like, I don't know, in some sense, I mean, I'm not necessarily trying to make a comparison in like magnitude of importance, but I don't know, it's kind of like when the internet was being created, and I guess I was too small to really remember, but like, I don't know, it was is creating the internet good or bad? I don't know. Like, I guess there's like a lot of good things that come with internet, a lot of bad things that come with internet. It shapes society in certain ways, or like changes the affordances of like, you know, how does power get centralized or non-centralized or whatever. And I think, like, I mean, but it also depends a lot on how the internet actually ended up really looking, and like, I don't know, how it got structured into people's
Yeah,
lives.
that's a very good comparison. I mean, a general base technology, then people can misuse it or use it properly. So that would happen with this too.
Right.
Eventually.
Yeah, and I don't think anybody can really, or I don't know, like, even with the internet, how could you anticipate the effects of the internet? Like, I mean, I think like ahead of time, if you were to just sit down and think about it, like, I think it would be very hard to, I mean, you could say, oh, this is going to be the end of humanity, or you could say, oh, this is going to be utopia or something, right? And like, both seem like plausible positions in some sense, right? And I think that, I don't know, of course, I don't know, the reality is somewhere in between, potentially, or I don't know, most likely. And I think like maybe that's the case here too.
Yeah, I agree. Yeah, there's a lot of path this can take here eventually. Great. So, Chung, any more question?
Well, you really work in a very dynamic area, and it would be very exciting. So probably before you wrap up your PhD, probably you would have made some dramatic changes.
Yeah, no, it's definitely an area in which a lot of stuff is happening. Yeah, it's kind of yeah, it's, I don't know, it's a lot. Yeah.
Great.
All right, thank you much for your presentation.
Cool, yeah.